Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about why free energy is considered free. So the change in free energy of a chemical reaction that actually represents the maximum amount of energy that's available or free to do work if the change in the standard free energy of a reaction is negative. So this idea of free really means available. Like, for example, if I say, hey, are you free this weekend? It means, are you available? Do you have available time to do something with me over the weekend? So in this case, when we're talking about free energy, we're talking about the energy of a reaction that is available to do some sort of work, right? So, for example, you can hook up a battery to a motor, and the motor will run. So the chemistry or the chemicals in the battery, the chemical reaction that is going on, is releasing energy. Some of that energy is going to do work in the motor to get the motor to run. So that's what we mean by free energy, how much energy is available to do some sort of work. So, for example, if we look at this reaction here, so solid graphite, carbon, reacts with hydrogen gas to form CH4. And so if we balance the equation, that should be a 2 there. So we see here that the enthalpy of the reaction, the heat of the reaction, is negative 74.6 kilojoules. So it's negative, so that means it's exothermic. Heat is being released, or energy is being released by the reaction. The change in entropy of the reaction, the standard change in entropy of the reaction, is negative 80.4. So it's decreasing in entropy. So the system is decreasing in entropy. So this means that in order for this reaction to be spontaneous, the overall increase of the entropy of the universe has to be positive. And so you'll notice that this is negative, so it's releasing heat or releasing energy to the surroundings. And so some of that heat has to go into increasing the entropy of the surroundings. And so therefore, that some of that energy that's being released here has to go into increasing the entropy of the surroundings. And so that's why not all of the energy is going to be available to do work, because some of it has to go into increasing the entropy of the universe by increasing the entropy of the surroundings. So remember, the heat is going out into the surroundings and it's becoming more dispersed, and therefore increasing entropy of the surroundings so that it will overcome or be more than the decrease in the entropy of the system. And so you'll see here that the delta G, the change in the free energy, the standard free energy of the reaction, is a negative 50.5 kilojoules. So notice that the amount of energy that's available to do work is less than the amount of energy released by the reaction. So because some of that, if you do a subtraction, about 24.1 kilojoules of energy is used to increase the entropy of the surroundings so that this becomes available. So this is less than this. This is less than this. So here, this is the available energy. But you got to remember that this is a theoretical limit. So the change in free energy represents a theoretical limit to how much work can be done by reaction. So in a lot of times it's less than that, right? So the amount of energy available to do work is even less than the delta G of the reaction, the standard free energy change in the reaction. Because why? Because even more energy is lost to the surroundings as heat, right? So take it for an example, a battery. I have here written that only reactions that reach the theoretical limit, the only reactions that reach the theoretical limit are those called reversible reactions. So what are reversible reactions? Those are the reactions that that can go with only an infinitesimal amount of energy pushing it one way or the other. So the example would be, say, the melting of ice at 0 degrees Celsius. So if you have an ice cube at 0 degrees Celsius, it only takes an infinitesimal amount of energy to add to that to get it to melt, right? So it's on the cusp, it's on the equilibrium of melting and freezing is at 0 degrees Celsius. So just adding a little bit of, just a tiny little bit of heat will push it to the direction of melting. So, or if you take away heat, it'll go in the direction of freezing. So that's what we mean by reversible. Um, so theoretical limits would only apply to those because they occur infinitesimally slowly, right? So that's one thing. They occur infinitesimally slowly because you're taking infinitesimally small increments of energy, you're adding or you're taking away. So the free energy is drawn out in an infinitesimally small increment. So if you were to like remove little by little over a long period of time, very slowly, then you would have a reversible process or reaction, and so therefore you would reach the theoretical limit. But in reality, in real life, that's not going to happen. So you're losing more energy. You're not going to reach that theoretical limit. So even though it says negative 50.5 is available, it's definitely less than that. So all real reactions are irreversible in this case. So in real life, we don't have reversible reactions. So for example, discharging of a battery. So if we take my example before of a battery that's being discharged, say it's hooked up to a motor and you are using the chemical reaction in the battery to run the motor. Well, some of that energy in the battery from the reaction is actually going through the wires and is lost as heat, because as the electrons are traveling through the wire, they're meeting some resistance, and so that's going to create heat in the wire. So some of that energy is going to be lost in the form of heat, and you can't get that back. So even if you recharge the battery, it's going to take more energy to recharge that battery than what was produced by the battery to run the motor. So therefore, we're always going to lose energy in the process. This is known as the heat tax, right? So there's a heat tax. You can't get it back if you lose your energy as heat. Um, so you could lower, right? You could decrease the amount of heat in the wire by like running the battery more slowly, right? Or letting a little bit go through. So the slower that it goes, the energy or the electrons go through the battery, the wires, less heat is produced, less energy is lost. But in reality, that's just not feasible. So you're always going to lose some more heat more energy in the form of heat than you can actually get back. So if the change in the standard free energy of the reaction is positive, though, so we've been talking about negative free energies, right? So if the negative free energy change is if the free energy change is negative, the standard free energy change is negative, that means that it's spontaneous. And so this is the limit to how much work can be done by the system, by the reaction. If it's positive, what that means is instead of a limit to how much work can be done, it's the limit to how much, with the minimum amount of energy that's required to make the reaction go, right? So instead of the amount of energy you get out of it, how much energy do you need to put into the reaction to get it to go? And again, this is a theoretical limit. It's going to be more than that for real reactions. So it's the minimum amount, it's the minimum limit. It's going to be more than that in real life. So you're probably going to need to put more energy than expected to get a reaction to go that has a positive change in the standard free energy of that reaction. So I hope this was helpful and clear and cleared things up for you. So if you enjoyed this video, if you learned something from this video, please hit that like button right over there, not down here, right over there. Share this video with others. Subscribe to my channel, hit that notification bell up there. And please put a comment down in the comment section. Let me know what you think. Thanks for joining me. Have a great day.